Thank you very much for having me here. Obviously, I'm managing the stress very well with this. That's okay. I would like to thank the organizer for having me presenting my work, even though it might be linked to the fact that Valentine is the president of the PCMI and I am her student. Or perhaps I have interesting results to show you. So I'd like to thank all of my collaborators with whom this work would not be possible. And thanks the entire PCMI for the very interesting conversations I had so far. Okay, so I will make a short introduction because I promised I would do it for the people not expert in this field. I'm studying the cold dense core, which is a phase in the star formation where we have, well, obviously very cold temperature up to a few kelvins. And we have indeed a very dense field. And it's one of the first steps of the star formation. So as you can see, it's just before the protostellar formation. And my PhD is focused on the study of the interaction between the ice and the gas phase. And ice is quite interesting to study because it needs complex the complex parameters to form. So we need like temperature down to 10 kelvins, which is matching the dense core conditions. But so far we had quite a few problems to study it from Earth because we can study the solid phase from the infrared wavelengths, which is a hellish nightmare to study from Earth because we have atmosphere. But now, as presented by Jennifer Noble, we have the James Webb Space Telescope, and with Ice Age, we should be able to get way more information on the cold cores. And one of the core that I will present you later today is being observed by James Webb. So why is it so interesting to study the grains? It's because certain molecules are mainly formed on the gray surface and not so well on the gas phase. And it's the case for methanol that I studied in depth in my thesis. So as I just said, methanol is observed in the gas phase, but the abundances we see in the gas phase, the abundances we see in the gas phase are way too high compared to the pathways we know. And this pathway does not account for how much methanol we are observing. So it seems that the main pathways are in the solid phases, which other molecules have been presented during this week. And we want to know how from the solid phase we go to the gas phase. Knowing that the temperatures are so cold, we cannot consider the thermal desorption. So we have a few mechanisms that we can use. A few have already been presented during this week. I'll list some. We have cosmic ray heating, chemical desorption, photodesorption, and sputtering by cosmic rays. And here we will try to define constraints on this mechanism efficiency and see how we got a few estimations. So the core I first studied was L429C. It's a cold dense core in the Aquila rift. So you have temperature going down to 12 Kelvin on the cores, the source. And we have densities which are superior to 1⁶ centimeters squared. And it's one of the few cores, well, now there are more, but it was one of the first which we had first observations of ices, which were done by with Spitzer by Bugert in 2011. And we added 30 meters observation of the gas phase, so we can really have the two informations on both solid and gas. So to do that, we used NOEMA and 30 meters from IM, and we obtained 3 millimeters maps of 300 over 300, 360 over 360 arc seconds with a velocity resolution of a few 0.2 kilometers per second. And well, unfortunately, we had NOEMA data that did not show evidence of small scale structure, and we couldn't take anything from it. So we just used the 30 meters data. And we had a total of 11 molecules detected. We had obviously methanol, OCS, CCS, HC3 CS, SOCO, isotopic logs of CO, a few lines of CN, and H2S. And then we have the ice observations done by Bogert, as I said. And you have here on the side the most solid detection of methanol. And this was on 4 positions only. And it was trying to observe the CF stretching mode of the methanol. So I want to emphasize the fact that there's only 4 positions of solid ices, but we are working on a proposal for the James Webb for the cycle 2 on this core to obtain, if possible, 100 more line of sight. So the first things I've done was to estimate the abundances of the gas phase. And it was done using a radiative transfer inversion code. And for that, we used the physical parameters of the cloud that we measured. And we created grids of parameters using the non-LT Radek code. And since we didn't have many lines detected for Radek, we had to add constraints for each pixel. And to do that, we used ROSA to compute the width of each line for each spectra. We used the temperature that was determined from Herschel data. And we used the American technique to compute the density of H2, assuming isotropy in the core. And finally, we estimated the Basel column density with a K2 test. And then we divided the whole map by the density of H2 to obtain maps as you see here. But if we take a look at the parameters through the visual extinction and density, we observe that most of the molecules seem to deplete at higher density, except for methanol. So our maps of methanol are very constant. There's no much variation between each pixel. And this, we try to understand how with chemical modeling this time. And we used the chemical model Nautilus that's being developed at the lab. And it's a 3 phases model, which is using gas surface and ice mantle. And we input the physical parameters that we already determined. And we add a cosmic ray ionization rate. And in the end, we get abundances of gas and ice as a function of time. So the code is available on this website. And we observed that most of the non-thermal desorption mechanism in Nautilus comes from the cosmic ray interactions with matter. So we had to add 2 additional parameters, which is a sputtering yield and a cosmic ray ionization rate. So we have, let's say, a grid of models, which are all depending of a series of parameters that you can see listed for each model. And to determine, so since Nautilus is measuring over timescales of 1 million years, we try to constrain which is the best time that is matching the observations the best. And for that, we use the distance of disagreement. And in the end, the only free parameter we have is the time. So you have an example here that the best time for each model is determined here between 10 power to the 4 to 10 power to the 5 years. So the result that we have on time is that it seems for all the models that it's decreasing with density for any set of model, considering low sputtering yield or high CR. And overall, the abundances are very well reproduced within a factor of 10 by the model. So now, if we study the budget of gas and ice in methanol, I would first consider the observations and then the model. Without surprise, we knew already that the reservoir of methanol was in the solid phase, which is, you see here in the first figure. It's only the ice abundances, and you can see that it's very high. And the observations are in black with the uncertainties. And in a second time, we try to determine the gas to ice methanol ratio. And for these 4 points, we have a gas to ice ratio, which is varying between 0.02% at low density and is increasing to 0.09% at high density. And so the first conclusion is that it is increasing with density for the observations. However, if you look at the models in the second figure, you see that we are not following the same trend as the observations, but I'll just come back to just the ices. We reproduce them well within a factor 2 for the high yield and a factor of 3 for the low yield cosmic ray. So for the trend, we still managed to have a gas to ice ratio that is matching a few data points. And one of our first hypotheses is that maybe this would be an indication that we have a change in the ice composition. So which means at lower density, we would have H2O ices. And then with increasing density, the mixture will come closer to a mixture of CO2 ices. Such change in composition could be possible and would occur during what we call the catastrophic CO freeze-out, which is the event where the CO will deplete on the grains. We also want to stress that we only have 4 observation points and we have strong uncertainties. And maybe if we had tens or hundreds of new line of sight, this trend might or might not be real. So the next step is to study L694, which is a cold core with a very similar feature as L429C. But this time it is more advanced. We are going in the infalling phase. So the matter is infalling into the core. And it is observed on this very preliminary evidences that the methanol is depleting at higher AV, which, if I remind you, in L429C, it stayed constant. We also have already points, background stars of with detection of methanol ices that were done by Jour et al. In 2020 from the ground. And as I said before, it is currently observed by James Webb. I think maybe the observations are already done. And we will have a set of data that we analyze soon. And hopefully, if Klaus dares to give me a few data, I will add that to my PhD. That's so far no answer. It's okay, I still have 1 year. But yeah, we already have done the gas observations with RM 30 meters again. That was done last year. And we identified a few molecules. So we already have N2H+, N2HD, CS and its isotopologues. We have methanol, also and its isotopologues, and then isotopologues of CO. And hopefully I'll get this data and keep working on this. So to conclude, we had observation of both gas and ices in L429C, and we could already compare these two things together. And in the first time, we showed that the gas abundances for most of the molecules show a depletion at higher densities, except for methanol. And if we look at the modelization, we need shorter time to reproduce the observation at higher density, but at contrario, we need longer time to reproduce lower densities. For the gas to ice ratio from the observations, we have the first estimation of 0.02% to 0.09% of gas to ice, and this is increasing with density. But as for the model, we have an opposite trend, and this time we make the hypothesis that it might be because of an ice composition changing in the cloud. But overall, in Nautilus, we noticed that the cosmic ray sputtering and cosmic ray ionization are the most dominant non-thermal desorption mechanism, and this will be the study will be done further by Amy Clément, which is in the room, starting her first year of PhD. And the next step is to study with a similar method, L694, and hopefully get the James Webb data before I end this PhD. Thank you very much.